I've had several questions asking about molar relationships, so I wanted to take a little time to explore how these work in a little bit more detail, hopefully to clarify this. So if we think about a simple binary compound like, I don't know, sodium chloride, let's just say, I think probably everybody has already sort of internalized this idea that the sodium chloride unit, if we have one molecule or one unit, that it contains one sodium plus and one Cl minus. And so similarly, 1 mole of NaCl has 1 mole, I'm going to stop doing the pluses and minuses just because I'm lazy, 1 mole Na and 1 mole Cl, right? So this one-to-one relationship seems pretty clear when we have something simple like 1 mole and something simple when we have sodium chloride. But as soon as we start going to different numbers, it can seem really confusing. So let's go ahead and stick with this nice simple sodium chloride, but go with some different numbers. So let's think about maybe like, I don't know, 0.229 moles of sodium chloride. If we have 1 mole of sodium chloride and 1 mole each of sodium and chlorine, that means that also if we have 0.229 moles of sodium chloride, it contains 0.229 moles of Na and also of Cl. So we use the cues from our molecular formula and the stoichiometry of how much of each element appears to be able to see what this relationship is. We can say that we have 1 mole of sodium per 1 mole of sodium chloride. Or we could say 1 mole of chlorine per 1 mole sodium chloride. That this is our molar relationship. We can also set this up in a systematic way to kind of do a unit conversion. So if we wanted to convert from 0.229 moles of sodium chloride and you had a question, how many moles of sodium are there in 0.229 moles of sodium chloride? When you have this simple one-to-one relationship, you might just be able to say, well, of course I have 0.229. But it's helpful to have a systematic way for when you have a more complicated scenario. So I'm going to use this ratio of the molar relationship that I just set up like a unit conversion. So I'm going to have my moles of sodium chloride. I want those to cancel out. So 1 mole of sodium chloride goes on the bottom and 1 mole of sodium goes on the top. And then this whole unit of moles of sodium chloride cancels out, and our answer is in moles of sodium. Now, I recognize that this probably looks really simple, so let's take a little bit more of a complicated scenario and see how it can be sort of handy. So, how about a different molecular formula, like calcium sulfate? All right, we got a lot of subscripts here. So if we were looking at 1 mole of calcium sulfate, let's imagine, well, let's just take a look, right? Our molecular formula shows us that we have 3 moles of calcium. We have to distribute this 2, so we would have 1 times 2 would be 2 moles of sulfur, and 2 times 4 would be 8 moles of oxygen. So we already can take this molecular formula and figure out what our molar relationships are. So now, when we try to convert a number, let's say we have a question that says, in 0.496 moles of calcium sulfate, how many moles of calcium do we have? So just like we did when we had this really simple one-to-one relationship, we're going to set it up systematically. We're going to start with that 0.496 moles of calcium sulfate, and now we're going to use that systematic relationship here to set up a unit conversion. And our units, we're going to go from moles of calcium sulfate to moles of calcium, because that's what the question is asking. So now we go right back up here and we see, okay, 1 mole of calcium sulfate has 3 moles of calcium in it. So I'm going to put my 1 mole here and my 3 moles here. And so now once again, our moles of calcium sulfate will cancel out, and our moles of calcium are what's left. So we will get 1.488, but we'll round that to 1.49 moles of calcium to keep our 3 significant digits. Okay, so what if you wanted moles of oxygen instead? You would set it up exactly the same way. Go ahead and take a second and do it. You can pause the video. All right, so right here, I'm going to put in my relationship that unit conversion just like before, only I have 8 moles of oxygen. So I get 3.97 moles of oxygen. If you want extra practice, you can check it with the sulfur as well. So this is a systematic way of looking at mole-to-mole relationships between a formula unit for a molecule or a compound and all of the different components that are in that compound. We can also use, actually I'm going to back up here for a second. I'm going to write this down. Do you remember that in our previous stoichiometry video, I talked about going from grams of something to moles of something using the molecular weight, and then we could go from moles to particles like atoms or molecules using Avogadro's number. So what we just did is very much like this kind of a conversion, but instead of using those conversion factors, we did something a little bit different. We went from moles of one thing, I'm just going to call that A, where A is the complete compound, in this case. And we went from that to moles of B, this other thing, and in our example, it was one of the elements in the compound. And the number that we used to get between those was just the formula unit, the chemical formula. So just like we did in our previous video where we could go from moles all the way over to particles, we can do that here as well. And we're going to do this exactly the same way that we did before. We're just going to use Avogadro's number. And depending on which kind of particles, how many particles you need, if you are finding out the particles for one of the components of the compound, like one of the elements of the compound, we're just going to apply Avogadro's number the same way that we did in the previous video. So let's say, for example, that we had a question like, how many atoms of oxygen are in 1.16 moles of aluminum oxide? So we're going to set it up using the skills that we just had. All right. So we're going to say we have 1.16 moles of aluminum oxide. That's the starting number that we have. And now when we look forward, we want to find out atoms. And we don't just want atoms or, units of Al2O3. We want specifically oxygen. So that means that we're right here, and we're going to have to take 2 steps. we're going to take our first step, which will be over here to moles of oxygen. That's our plan. And then we're going to use Avogadro's number to get atoms of oxygen. So our calculation will have two steps. So for that first step, we're going to use our relationship from the formula unit. We can see that in 1 mole of aluminum oxide, we are going to have 3 moles of oxygen. And if you want to do 2 separate steps, you can, but you can also just calculate this whole thing through. And so we have 6.022 times 10 to the 23rd atoms of oxygen in 1 mole. And if you write it out, your calculation, with all of these details in here, with the labels for the atoms, for the moles, you can see that our moles of oxygen will cancel, our moles of aluminum oxide will cancel, and now the units that we want, atoms of oxygen, are the units that we have left over, and that means that we've set it up right. So when we do this calculation, pause the video real quick and see what you get. I got 2.10 times 10 to the 24th atoms of oxygen. Hopefully I did this right, but please do tell me if I ever make any calculation mistakes in videos, because I do make mistakes, so I want to know about it if I had. So when we look at this number, I always like to double check and say, does this answer make sense? So let's think about it. We started with a big number already. 6.022 times 10 to the 23 is Avogadro's number. We're multiplying it by 3 and then by a little bit more than 1. So it needs to be a little more than triple the first number that we had. So if I think about 6 and I'm going to triple it, that would be 18. And so that means I'm going to go up 1 digit here from 23 to 24. That's good. And that would make this about 21 if I translated it times 10 to the 23rd. And that's a little bit bigger than 18 times 10 to the 23rd, which is my, starting guess with tripling. So this number does seem reasonable, and I think it probably checks out. All right, please let me know if you have any more questions about these moles. I'm going to start another video that shows you how to do relationships in the same way between 2 different compounds in a balanced chemical equation. So that's what's coming up next.